This is the last video for section 3.6. We're going to be classifying our harmonic oscillators. So remember, when we have a harmonic oscillator, we're going to have a second order differential equation like this. But unlike the generic one where it was just A copies and B copies, but a different B, and C copies of Y, here we've got mass, this is the damping coefficient, this is the spring constant, M and K must be positive, and B must be non-negative. B can be 0, but it cannot be a negative number, and M and K must be strictly positive. Okay. So, if I have this sort of a situation, my characteristic equation is going to be ms squared plus bs plus k is going to equal 0. So if I look at what the roots are going to be, s would be, just using the quadratic formula, the opposite of b plus or minus the square root of b squared minus 4mk all divided by 2m. Okay. All right, and so this, the b squared minus 4mk, is going to determine the number and the type of roots that I have. Okay. And basically there are 4 possibilities that we need to look at. If b is equal to 0, we would say this is just undamped, because the damping coefficient would be 0. That's the case where Moose, our massless mouse, just gets to go back and forth forever and ever and ever, because there's no friction or air resistance to stop that fun ride. Okay? If we have a situation like this, notice that that's going to ensure that what I have here, the b squared minus 4mk, is just minus 4mk. It's always going to be negative. Okay. And b is also going to be negative. So that would mean that s would be just a pure imaginary number. Okay. So it would be just, some number a times I. So the real part of the complex root would be 0. Okay. So when I have that, the origin is a center. If we pass to looking at the phase portrait for the corresponding system. And that explains what's happening when I got something that's just going around like so. That's capturing the fact that Y and V are both just oscillating without changing the magnitude of the oscillations and without ever stopping. Okay. The other possibilities are all going to involve B being 0, again, B being positive, because again, B is not allowed to be negative. Okay. But I could have B being bigger than 0, and I could have B squared minus 4mk being less than 0. If that's the case, then I've got a negative under the radical, so I'm going to have some complex roots. Okay. So I would have 2 complex roots that came in conjugate pairs, but I would have a positive, I would have a negative part here to the real part of things, because notice this is negative b over 2m plus or minus the square root of b squared minus 4mk over 2m. This would be the real part of my complex roots. It's a negative number. When we have a situation like this, we would say that this is underdamped. And the origin, if we looked at the phase portrait, is a spiral sink. So my phase portrait would look something like so. So we've still got a lot of oscillations going on. It's just those oscillations are getting smaller and smaller and smaller, approaching the origin. Okay. All right, I could have that b is bigger than 0, and b squared minus 4mk is bigger than 0. It could be positive. Now, if that's the case, I'm going to have real roots instead. In that case, we would say that our system is overdamped, and the origin is just a sink. My phase portrait would look something like this. I'd have my straight line solutions that were approaching the origin, which was my equilibrium solution, and my other solutions would start like so. So they really wouldn't be oscillating back and forth the way we have if it's underdamped or undamped. Okay. And of course, the last possibility is that B could be bigger than 0, and B squared minus 4mk could equal 0. Okay. When that's the case, we have just one root, because this would be 0. So our one root would be negative b over 2m. It is still negative. Okay. If we have that, we're going to say that this is critically damped.